So the dipole moment of oxygen being negative will repel other oxygen molecules. The dipole moment of the hydrogen being positive will repel other hydrogen molecules. This will result in a crystal lattice, a separation of these different charges and expanding the molecule as temperatures decrease. As your kinetic energy decreases at lower temperatures, the interactions between the polarity, the positive and negative charges of these water molecules will take over, and you will have charge repulsion being the more dominant force than kinetic energy slamming one molecule into another. So the density of water will decrease past 4 degrees Celsius, from 4 to 0. 4 degrees Celsius is the densest liquid water will be. The densest any form of water will be. So anywhere from 4 to 0 degrees Celsius, liquid water decreases. It goes from 1 gram per cubic centimeter to like 0.998 grams per cubic centimeter. But as soon as it hits frozen solid water, it goes from 0.98 to like 0.91 grams per cubic centimeter. It goes to like 9-ish, 10-ish% less dense. So ice will float. The freezing geometric pattern gives the solid form of water lower density than liquid form, and ice will float. And ice is a good insulator for heat, so when ice floats, it will form a layer of ice, and you'll have a liquid water layer underneath. And if the means by which you lose heat is through the surface of the water, then that means you can't lose heat through the liquid water to the surface because there is a layer of ice between you and the surface. So that's why building an igloo will keep you relatively warm, why you can go ice fishing and still find anything but fish sickles in the water underneath, etc. Now, we'll move on from water for a moment and discuss macromolecules. I'm going to give a brief overview. First, let's talk about what a macromolecule is. Macro is large, molecule. A macromolecule is a very large molecule that is commonly created by the polymerization of smaller subunits. They are typically composed of thousands or more atoms. Let's briefly discuss the function of each of the primary 4 types of monomers. Type 1, carbohydrates. Carbohydrates are things like sugar and fiber. Lipids are fats, oils, waxes, and steroids. Hormones like testosterone are also lipid-based hormones. Amino acids are proteins, enzymes, and hormones are what amino acids build. Amino acids are the building block of these larger macromolecules. And then we have nucleic acids, which are the building blocks of DNA and RNA. So, a carbohydrate will generally have the structure of CH2O, the formula, not the structure, excuse me. We generally have the chemical formula, the empirical chemical formula of CH2O. We have a problem. This is formaldehyde. That's not particularly tasty. That will make you go blind and, well, eventually crazy and stupid and kill you. So, formaldehyde is a problem, but it is technically a carbohydrate. So, what we're primarily going to be discussing is we're going to be discussing sugars, which will have a basic chemical formula of C6H12O6. This will be our glucose, our fructose, our galactose. Fiber is typically, when we discuss fiber, we're going to be referring to cellulose, which is a chain polymer, a single chain polymer with no branches of glucose. Beta glucose most typically. That's usually what we'll talk about when we discuss fiber. Now, lipids, our fats, our oils, our waxes, they're going to be primarily hydrocarbons. Carbohydrates contain carbon, hydrogen, and oxygen. Hydrocarbons will typically just be carbon and hydrogen. So CnH2n will be our typical 2n plus 2 would be our typical chain form of just a straight carbohydrate, just an alkane, for example. But oils, fats, these are all going to be long chains of hydrocarbons. Waxes are going to be the combination, the ester combination between two different fatty acids or oils bound together at their heads. Steroids are typically going to have a tetracyclic structure, which means a 4-ring structure. And hormones like testosterone specifically, has a tetracyclic ring structure. It is a steroid hormone. Cholesterol is also a steroid compound. Now, amino acids. Amino acids will typically have a similar function that I described before. You'll have your amino group, which will be your amine. So this will be NH3 positively charged, moving to an alpha carbon, which will have a hydrogen, and a R group, which can be variable. And then you'll have your carboxylic acid group, CHO-. Now, the uncharged version of this is to remove the hydrogen and add a hydrogen over here. So this is just carboxylic acid and an amine group over here. All right? So this is your basic structure of your amino acid. Chaining these in sequence from amino to carboxylic, amino to carboxylic, amino to carboxylic, that will get you your polypeptide chain. Proteins are polypeptide chains. They have a bunch of different forms, but enzymes are proteins with a job to do, and hormones can be also in protein form. Insulin, for example, is a proteinaceous hormone. Nucleic acids. Nucleic acids will typically have the structure of a phosphate group, a 5-carbon sugar, and a nitrogenous base. So that will be your typical structure of your nucleic acid. Nucleic acid, or your nucleotide, excuse me. Nucleic acids are the long chain forms of DNA and RNA, which are composed of many nucleotides. So, this is oversimplified for now, but let's talk about our most important chemical reactions in Cambridge, the condensation reaction and the hydrolysis reaction. Yes, this is blurry. That's not the camera. That's actually the slide. It is actually blurry on the screen. So, in our condensation reaction, we have 2 sugars, 2 carbohydrates that undergo the condensation reaction. Water is removed, and a glycosidic bond will form. In our hydrolysis reaction, or our hydrolytic reaction, we will have 2 sugars that are bound together as a disaccharide. Water will be added. This disaccharide glycogen bond will be broken, and you will have, at the end, 2 separate monosaccharides. This reaction, these 2 reactions, can apply to any macromolecule. Remove water to create and to form a bond. Add water to break a bond. When you are doing this, it is important to redraw the structure of whatever it is you are drawing. So if I am going to do this, I will redraw the structure. Here, I'll draw this, I'll draw this, I'll draw this oxygen here, I'll draw this carbon over here, I'll draw this carbon over here. This is CH2OH. This is going to be our hydrogen. Oops, that looks terrible. This is going to be our hydrogen over here. This is going to be our hydroxyl group over here. This is going to be hydroxyl. This is going to be hydrogen. This is going to be hydroxyl. This is going to be hydrogen. This is going to be hydroxyl. This is going